The announced title is there, the minimum circuit size problem. I'll tell you what it is, and especially I'll try to convince you that there's a reason that we should care. And I'm really going to go back to a theorem that I guess everybody here knows, the Cook-Levin theorem. Namely, that the satisfiability problem is NP complete, although, of course, NP didn't really exist as a notion until they isolated it, and it certainly didn't have that name yet. But what you might not know is that, I guess people do know some of the history. Cook was over here in this hemisphere, reasonably well-known mathematician and computer scientist, and done other work that was widely known in North America. Levin was working in the Soviet Union, not much contact with what was going on in the US, and it's a little bit remarkable that this happened at roughly the same time. But the part of the story that I think is less familiar to most people is that Levin delayed publishing his results because he wasn't really all that fired up about the satisfiability problem. He thought it was an interesting problem, but the problem that he really was interested in was this one, the minimum circuit size problem. And there's always a chance that I misunderstood the conversation, but Levin did tell me that he delayed publication of his results because he really wanted to nail the complexity of the minimum circuit size problem. So now it's time for me to tell you what it is. MCSP takes as input two things. One is the entire truth table of some Boolean function. So let's say that f is just a bit string of length 2 to the k for some k. Just telling for all of the 2 to the k strings of length k what value the function takes on that value. And some number which I'll sometimes call threshold, or let's just call it I. And the question is, does f have a circuit of size less than or equal to I? And you can see that this is a question that people working on Boolean circuits and just in general Boolean computation would be interested in. You know, if you're given a truth table, the way maybe some of you have been given a truth table in some computer architecture class and told to find a small circuit for it, you know, there are techniques, Carnot maps, that work for circuits of depth 2 if you're trying to build a DNF. But they quickly become unworkable if you're trying to work with very many variables. And already before complexity theory had really taken off as a discipline, in the Soviet Union, there was interest in this problem and in general sort of I'll say a vaguely defined notion the Russian word perabor was something that they were really interested in. The problem is said to require perabor or brute force search if the only way you can solve it is just by looking at all possible solutions. And in fact, there was some work that had been done. There's a wonderful survey by Trachtenbrot that I can point you to later, describing the atmosphere in the Soviet Union and why, in fact, there was a body of work that was considered by some to show that this problem, the problem of figuring out what the size of a smallest circuit is, requires parabola, that the only way that you can solve this is just to do a brute force search. If that were really established, then in fact we would know that P is not equal to NP, because this is pretty obviously a problem in NP, because you're given the entire truth table, and so K, the length of the input, is just logarithmic in the length. The length of the input to F is just logarithmic in the length of the thing that you're looking at. And so you can just guess a circuit of size I, because there's no reason for I to be any longer than the size of the circuit. Every truth table has got D and F of size roughly the same size as 2 to the K. And then you can just verify for all of the linearly many inputs that the circuit is doing the right thing. So it's clearly in NP. And if you could prove that the only way to answer this question requires more work than, requires essentially the amount of work of searching through the entire search space, then you would have shown that this problem lies outside P. So clearly the work that had been done did not really show that this problem requires parabola. And Levin was certainly keenly aware of this work, and it bothered him, and he wanted to nail the complexity of this problem. Well, now it's about 50 years later, and we still don't know what's going on with this problem. So it's good that he didn't really delay until the problem was really solved. What do we know? Unfortunately, not a whole lot. As I say, it's still open if the problem is NP complete, but if MCSP is easy, and by easy, maybe I will mean in polynomial time, or more often, i.e. if MCSP is in P poly. Should I define what P poly is? Yes, thank you. P poly, we're going to be putting up a bunch of complexity classes, so let's get a list going. Here's P. Don't want to put it at the bottom because we're going to need some smaller things. And here's NP. P poly sits over here kind of close to P, but what it is, it's the class of all sets A, such that A has poly-size circuits. In other words, for each input length, there is a chunk of hardware, which I'll usually draw as a triangle. It has n inputs, and it outputs a single bit, and it says yes if the input is in A, and no if it's not. Okay, so it's a natural notion of what it means to be easy to compute if you don't have your notion of computability based on programs, but instead you want to know how much hardware do you need in order to compute this function. There's all kinds of non-computable stuff in p-poly. So non-computable in the way that we think of computability theory. So for instance, if you know what the halting problem is, let's say the set of all x such that Turing machine x on input x halts. This is the classic example of something that's not computable. But it remains not computable even if we pick a very inefficient encoding of it. And it's still a trivial observation or an important observation in computability theory that this is not a computable set. But for every input length, there's certainly a trivial little piece of hardware that just checks to see if the input is all zeros or not, and either accepts, outputs 1 if the answer happens to be yes, this thing halts, or outputs 0 otherwise. We don't have any way to build the circuits, which is why it's not computable, but certainly combinatorially, in terms of the pieces of hardware that you need, this is very easy to compute. So everybody's clear on what p-poly is now, right? So if MCSP is in p-poly, then there is no crypto. In other words, there is no cryptographically secure one-way function. So this is a pretty strong reason to think that MCSP is hard. And this is one of the results that we will prove later. What's another thing that we know? If MCSP is NP complete, and I'm going to be specific about what kind of NP completeness we're talking about. If it's NP complete under polytime M reducibility, which, if you took any class in complexity theory, this is probably the notion of NP completeness that you studied, then exponential time is not equal to ZPP. Okay, if you didn't know what p-poly was, my guess is you don't know what ZPP is either, and so let's give a definition. Some other complexity classes that we need to know about. So, inside NP, there's a complexity class called RP, which is one of many ways to formalize probabilistic computation. RP stands for random polynomial time. And the way to think about this is you've got this NP machine. If it accepts an input, that means that there exists an accepting path. And if it rejects, all the paths are rejecting. For RP, if there's any accepting path at all, then there are a whole lot of them. At least half of them. So in particular, a randomly chosen sequence of coin flips will cause you to accept with pretty high probability. And if you repeat this a few times, if there's any, if the thing is accepted, then with very high probability you'll discover that pretty quickly. I should redraw this. Because everything in RP is easy in this non-uniform sense. And this is a very easy, simple fact that we'll need a similar proof later on if we are able to cover everything. But right now you can just keep this in your mind. But what's ZPP? Sitting underneath RP are the things that have both RP and co-RP solutions. Co-RP is just the complements of things in RP. So we have this containment. And this class is what's called ZPP. ZPP stands for zero error probabilistic polynomial time. What's the reason for that? Because here you get a proof if something is in the set. Here you get a proof of something that's not in the set. And if you just try things at random, pretty soon on your input you're either going to find a proof that it's in the set or a proof that it's not. And so very quickly you'll have a way that gives you a completely reliable zero error answer. And that's where that name comes from. Okay, so back to this theorem. If MCSP is NP complete under the type of reductions that you're familiar with, then X is not equal to ZPP. On the face of it, this is a really uninformative implication. This is like saying if something interesting is true, if MCSP is NP complete under polynomial time many-one reductions, then Earth is a planet. I mean, this just has to be true. We can't prove it yet, but the conclusion here is something that we expect to be true, and thus the fact that this controversial assumption has a completely non-controversial conclusion doesn't tell us anything about how likely this is to be true or false. What it does tell us is that it's very unlikely that we're going to be able to prove this anytime soon, because this is a really long-standing, very important open question. Are there things in exponential time that require a long time to solve probabilistically? So let's just draw X way up there. Okay, this is one of the goals that we have. Yes?
I have a question about the previous.
About the which?
The first result that you
yes.
mentioned about if you had a polynomial time algorithm for this, then you can't do crypto.
That's right.
So since we care in crypto about how fast you can break it, right, quasi-polynomial time. So if I had does this thing show that if you have a T event time for MCSP, then you can break crypto in T event time?
Roughly, yes. Everybody hear the question and answer? Okay. Another result that we want to give: if MCSP is hard for TC0 under AC0 M reductions. Let's call this uniform AC0. Then NP is not NP poly, and let's just say this way: the polynomial hierarchy, there exists an epsilon greater than 0, exists an A in the polynomial hierarchy such that A is not in size to the epsilon n. More things that I'm throwing at you. Talking about if NP is NP poly, that much we understand. What's this polynomial hierarchy thing? Well, both of these things are contained in P to the NP, which is contained in NP to the NP, and then you've also got co-NP to the NP. And this whole hierarchy of things that you can define is called the polynomial hierarchy. If you've seen this before, this is boring and obvious. The reason I wrote it really small here is because I really don't have time to explain this if you haven't seen it before. But it's a well-known complexity class that's sitting there just above NP. So I've explained what these things mean. What's TC0? TC0 you can think of as, actually I'm going to put it down here, a very small complexity class. To motivate TC0, I also need to tell you what AC0 is. AC0 is a really tiny, tiny complexity class. This is so tiny that the main interesting theorem about it is that circuit families in AC0 can't even tell if the number of bits that are 1 in your input is odd or even. That's the so-called parity function. In terms of models of computation, it's what you can do with polynomial-sized circuits. So it's NP poly. Oh, but you can also build them very efficiently, which is why they're called uniform. Uniform just means we can build them, it turns out, extremely efficiently. I'm not going to go into the details about how extremely. So these are circuits where the depth is constant. You've got unbounded fan-in ands and ors, and the depth is the distance from input to output, and the depth is constant. So let's say you've got a circuit family where all the circuits are of depth 8, or another circuit family where all the circuits are of depth 120. You know, as long as there's some constant, that is that's what you get for this class AC0. TC0 is defined the same way, except that the circuits are now composed out of majority gates, where a majority gate is just a gate that turns on if more than half of the wires feeding into it are 1. And this was initially studied by people who were trying to determine what can you do efficiently with the neural net model of computation. Because a neural net is basically a bunch of majority gates wired together, and often you're focused on things that have fixed small depth, 3 or 10 or 20, some sort of fixed depth. So that's what TC0 is. I haven't motivated these classes very well except to say, oh, they're really tiny. The real motivation comes from this notion of reducibility. The real success that, I didn't erase. No, this is me. Okay. But we don't need this anymore. The real success that complexity theory has had, certainly it's not in proving that a lot of problems we care about are hard, because those are still open questions. The success that complexity theory has had is in taking this universe of computational problems where each dot here I'm marking on the board is just some function that we care about, and grouping them together into equivalence classes of things that are equivalent because they're interreducible. And some of these are really important, like the class of things that are complete for NP. But if you're using polynomial time reducibility as your tool to classify problems, then it's useless in drawing distinctions among problems inside of P, because any two problems in P that just is one big equivalence class. But there is a lot of interesting stuff going on inside of P. And in order to elucidate that, people use more restrictive reductions. So a lot of people in their complexity classes learn about log space reducibility, which is very useful. But there's a lot of stuff going on inside log space. For instance, TC0 is a small subclass, we think. There's definitely a subclass, we think it's a small one, of log space. And so people have looked at even more restrictive reducibilities. And AC0 is so restrictive that we know that it's really weak. And so when you prove that something is complete under this really restrictive notion of reducibility, then you actually can get sometimes real lower bounds out of that. And the benefit, in addition, is that these equivalence classes, like all of these NP complete problems, essentially all the ones that we care about are also complete even under this really restrictive notion of reducibility. So we don't lose anything by looking at these uniform AC0 reductions. And if you modify the notion of reducibility just a little bit, in a way I'm just going to lie and smooth over right now, the complete problems you get for TC0, just to show you what kind of problems we're talking about, the complete problems are sorting, and multiplication, and division, some fairly important computational problems, and certainly just the majority function itself are all complete for TC0. So one reason we care about complexity classes is what are the complete problems? What problems that we care about does the class help us understand and fit into a framework? Because TC0, in that sense, helps us understand some important problems. So now I've defined all the terms for this theorem. If our problem, MCSP, is hard even for this tiny, tiny complexity class, if it's hard under this really restrictive notion of reducibility, then you get lots of, again, unfortunately, consequences that we think are true. So once again, this doesn't give us any reason to think that we know the truth or falsehood of this hypothesis. It just tells us we're not going to be able to prove it anytime soon. One more theorem along this same line that we want to put down here, something that we hope to cover in this 90-minute lecture. If MCSP is hard for, again, tiny class TC0 under, let's call it, time cube root of n local reductions, then false. So in other words, finally, if you make the class of reducibilities restrictive enough, then you do get a non-completeness. Not only is it not NP complete, it's not even hard for this tiny complexity class. Now I should tell you what a local reduction is. All the reductions that we're talking about take some input and map it to an output. For AC0 reductions, there's hardware sitting in here that's just constant depth, ands and ors. For a local reduction, each bit of the output, if I want to compute it, I can, in a very small amount of time, much less time than the length of the input. So I don't have time to look at the whole input, but I can figure out a few bits that I want to query and read those few bits and figure out what the answer is. So that's what a local reduction is. Each bit just depends on a few bits. That's the locality. And that we can compute those quickly. And you see, well, why would anybody care about such a really restrictive notion of reducibility? Well, again, in that diagram that I just erased cleverly, most of the NP-complete problems, not all of them, but a lot of them that we care about, are complete under this notion of local reducibility, where in fact the amount of time that you need is not cube root of n, but just log n. So, you know, with a tiny, tiny amount of time, you can query a small number of spots and compute the answer. And this is actually a crucial tool in a number of results about, in particular, exponential time that we won't end up needing to say more about, except that it is an important and well-known notion. But while I have that diagram up here, there's another notion of reducibility I'm going to put down here way at the bottom because it's so small it hardly doesn't even deserve to be called a complexity class. An NC0 function is a function that is computed by circuits where each bit of the output depends on just some constant number of bits of the input. You know, 15 bits or something. And you can talk about uniform NC0, but you can also talk about non-uniform NC0, where the circuits computing the reduction exist, but there's maybe not an easy way to find them. And in fact, the reason I'm introducing that now is the final theorem that we might want to talk about is if I'm going to put this in quotes, MCSP in quotes, and when I say MCSP in quotes, I'm doing that because I mean something that's not MCSP but looks sort of similar. If MCSP, there's no if, MCSP is hard for debt under NC0 M reductions. What's debt? It's this other complexity class I left room for in this diagram. It's the class of things that are reducible to computing the determinant of integers. Certainly that's an important problem, and it turns out that there are a lot of interesting things that are complete for this complexity class det. So it's one of the more important subclasses of P. So this is the roadmap for what I hope to cover today. There's a good chance I'm not going to get through all of it. How many people want to vote for number 2? 1, 2, 3, 4, 5, 6, 7, 8, 9. So everybody else is voting for number 3. Now, this is maybe unrelated, but 1 over pi has this decimal expansion. And just by coincidence, this sequence happens to be recording if those digits are odd or even. Does anybody want to change their vote? Nobody wants to change it? Okay, thank you. Because this would never, never, ever happen. Why not? What is so odd? I mean, why? Maybe there's a really a crazy reason why this one would never happen either. Well, Kolmogorov's insight was to quantify the amount of information that's in a finite object. Given any string x, the Kolmogorov complexity of x is defined to be the minimum of the length of a description such that D is a description of x. But what does that even mean? What does it mean for something to describe x? Well, given any Turing machine, which I'll just call U here, we can say U is something that uses D as a description for x. And this is at least a mathematically precise definition. You're given any machine U and any string x, this is either x is not in the range of U or this number is existing. And Kolmogorov's insight was, if you pick any 2 universal Turing machines, where a universal machine is just one that simulates programs. It takes as input a description of a machine and some other input, and it runs that machine on that input. If you take any 2 universal machines, this quantity will be roughly the same. So if you just pick some universal machine and say, okay, I'm going to define Kolmogorov complexity in terms of that, then this is a meaningful definition. There's something a little bit arbitrary about the choice of U, but if you were to pick another universal machine, the amount of information that would be said to be contained in that string would differ only by some additive constant, which means that they're essentially agreeing. So it's a meaningful definition, and we say that something is random if the Kolmogorov complexity of x is greater than or equal to the length of x, or maybe we'll say the length of x minus, I don't know, 10. Because if you say that the description length has got to be nearly the length of the input, then a huge percentage of all strings will be random. Whereas this one and this one are just not going to be random. You know, things that have really short descriptions cannot be sensibly called random in the sense that if you look at the probability of getting something whose description is much less than the length of x, you know, that the probability of landing in that set is just tiny, which is at least a mathematically meaningful way to give a definition of what it means to be random. And in fact, there is no other really satisfactory definition that people have come up with. So this notion of randomness, meaning it has no short description, is something that we're going to use. Why am I talking about this now? Other than the fact that Levin's advisor was Kolmogorov. Well, think of a truth table, you know, a bit string as just being a truth table. If it's got a small circuit, well, what is that? It's a short description of the string, a short description of the truth table. And so in the environment in which Levin was working, certainly Kolmogorov complexity was in the air, and people realized that there was some vague connection between the minimum circuit size complexity problem and Kolmogorov complexity, because they're both talking about short descriptions in some sense. But Kolmogorov complexity is not computable, whereas the minimum circuit size problem is in NP, so it's computable in exponential time, which in the larger scheme of things means it's very, very computable. And so Levin, at the same time as he was doing this other work, came up with a time-bounded version of Kolmogorov complexity, which is the minimum length of description plus log of the running time such that u of d is equal to x in time t. You might ask why the log of the running time. If I had more time, I would go into that. But for now, let's just say it's because it's the right thing to do if you're trying to understand the complexity of problems in NP. But it's really not the right thing to do if you're trying to understand circuit complexity. And again, if I had more time, I would describe exactly how to modify things so that this definition makes sense. Instead of adding the log of the running time, we just add the running time. Well, I just go ahead and write it such that we still want D to be a description of X. But since we're adding the entire running time, we're going to use some of this idea about locality of computation. Instead of describing, writing down all of X, we just want to figure out what the ith bit of X is in time t. So you can have a short description along with a little extra information there. Oh, of course, we're still using this arbitrary universal Turing machine. Well, there's actually a penalty that we pay for that. Right? If we say, without the time bound, KU
of x is equal to k u prime of x. Oh, that's plus or minus some constant. Well, with Levin's definition, ku of x is equal to ktu of x is equal to ktu prime of x plus or minus. Well, it's actually like order log n. And with kt of x, with machine u, you get the same value as on u prime, plus or minus. Well, we can't even say that. You know, it's order this times log kt u prime of x. In other words, but still you get roughly the same value, but it's a lot rougher notion of roughly. Still, it's close enough so that kt of x is equal to the circuit size of the truth table given by x, you know, within a, let's say, less than or equal to actually I forget if it's exactly q, but some polynomial relationship there. So it's not exactly the same thing as circuit size, but it's kind of the same thing. And it turns out that this kind of the same thing is useful enough for a lot of applications. Whereas Levin's notion of time-bounded Kolmogorov complexity is also related to circuit size, but of unusual types of circuits. With Levin's notion, this is less than or equal to size of x cubed, but I'm putting the superscript e here. What's this mean? Yes?
So what's exactly the size of x?
I'm looking at x as the truth table of a function,
Oh,
and I just want to know what's the circuit size. Which means I'm really just punting the question, because what's the size of a circuit? Counting the number of gates, that's a popular measure. Or the number of wires, that's kind of the same thing, maybe not exactly the same thing. Oh, what's a gate? Are we going to allow just fan-in-2 ands and ors? Are we going to allow unbounded fan-in circuits? Well, these are all reasonable questions. They all give a different notion of size. And, you know, I might change the exponent here, but it's still going to be roughly the same. And what is this thing that Levin's time-bounded complexity is related to? Size superscript e? Well, let's draw a picture again of a circuit. We've got AND gates and OR gates. We're going to allow a new type of hardware, which is an oracle gate that takes a bunch of wires in it. And if this string that feeds into that oracle gate is in the set A, it'll output 1, otherwise it outputs 0. And if A happens to be complete for exponential time, I'll call that E. So in other words, Levin's notion of time-bounded Kolmogorov complexity is really useful. It's a great definition, but it corresponds to circuits that are weird circuits, right? They're not ordinary circuits. They're circuits that have this extra piece of hardware that's computing something that's hard for exponential time. We're going to use that too. We're going to be making use of this funny notion of oracle circuits. Okay, so we've introduced time-bounded Kolmogorov complexity. We have MCSP, where CS is circuit size. That's just one notion of complexity. We can stick in another way to measure the complexity of an object, like KT, and we get a new problem. And that's what I meant when I said this thing that's not really MCSP, but is something kind of similar. So now we have a more precise roadmap of where we're going. But I haven't really told you why this is useful. And the reason that this Kolmogorov complexity framework is useful is that this theorem and another theorem I didn't even bother to put up here, MCSP is hard for SZK under BPP Turing reducibility. I'm not even going to really define what this notion of reducibility is. BPP is yet a third notion of probabilistic polynomial time that is also contained in P-poly. It's just another way to talk about efficient things you can do probabilistically. Oh, this class SZK is, let's draw it here. Certainly, well, actually, no. I mean, it's not really above RP. It's just this other complexity class, but it's got a whole lot of cryptographic things in it. So it's a well-studied class. SZK stands for statistical zero knowledge. If some other place you've heard about zero knowledge proofs, this class arises there. Okay, so this hardness result and this one and some of the other results too are proved. Basically, the most important hardness results we have, the best evidence we have that MCSP is hard, uses this one proof technique that comes from pseudorandom generators. So we don't need this anymore. I'm going to tell you about pseudorandom generators. A pseudo-random generator is just a function that takes a short seed, let's say a seed from the length of the seed might vary, but in most cases here, let's say into the epsilon, and maps it to outputs of length n. So we take a short seed and we produce a long output. And the output is supposed to be something that looks random. What does it mean to look random? We say that G is secure if for every efficient test, and by efficient, let's say for every T in P-poly, for every algorithm that you can implement with polynomial-sized circuits, for all n, the probability over random x in sigma n that t on input x says 1 or accepts is roughly the same thing as the probability over every seed of this much shorter length that t on g of s is 1. So in other words, if you're trying to distinguish between the situation where you're looking at a truly randomly chosen phenomenon, or where you're looking at is pseudorandom noise that's being generated from a short randomly chosen seed, then your test really shouldn't be able to distinguish between them. The probability should be roughly the same. There's a large literature on pseudorandom generators. A lot of great work has been done. One theorem that we'll be using, the Hostad and Pagliazzo-Levin-Luby result, says that if f is a cryptographically secure one-way function, then a particular generator that we can build from f is secure. Secure. So you can build a secure pseudorandom generator using this recipe that's provided where you plug in a cryptographically secure one-way function. So it's a function that's computable in polynomial time, hard to invert on a big fraction of the inputs. And if you know what a pseudorandom function generator is, we need that too. I'm not even going to bother to write the definition on the board. I'll just pretend that the intuition I'm going to hand wave about with pseudorandom generators is really sufficient, whereas in fact you need a pseudorandom function generator. So with this vague intuition, we can explain what the connection is between Kolmogorov complexity and hardness results. How do Hostad and Pagliazzo, Levin, and Luby, the same Levin, by the way, prove this result? Well, they show that if T distinguishes random and pseudorandom for this generator G sub f, then F inverse is, I'll put computable in quotes, in BPP relative to test T. So what does this really mean? This means that you've got this BPP, a probabilistic polynomial time machine, M, that is given f of x. And what does it do with that? Well, it uses this oracle that's distinguishing random from pseudorandom somehow, and it computes something so that if I apply f to that, it's computing something in the pre-image of f of x, I'll get f of x back. So it's inverting it with high probability. Doesn't necessarily always get the answer, but it's getting it with reasonably high probability. And Tsai and Cabinets were the first ones to make this connection. And what you have there is that if MCSP is easy, well, wait, what's the connection here with MCSP? Remember, the pseudorandom generator is taking short input and quickly producing long output. So the output is something that's got a short description, which means that if you can look at a string and figure out, oh, is the time-bounded Kolmogorov complexity of this high? Well, then, for a randomly chosen string, the answer is going to be sure. Just about everything's got high complexity. Whereas if it's a pseudorandom output, the answer is always going to be no. And since we can make n to the epsilon, if we can make epsilon really small, that means that asking if kt is high or low is also telling us something about the circuit size of Z, because they're polynomially related. So that's why using MCSP as an oracle, you can accept a randomly chosen string with extremely high probability. So this probability here is going to be close to 1, and this probability is going to be 0. It's a terrific test to distinguish random from pseudorandom, and it's going to break every possible pseudorandom generator. Therefore, it's inverting. You can use it to invert any one-way function. There is no crypto. Is that argument clear? Clear enough? Any need for me to elaborate on this? Okay.
Yeah.
Yes.
Just, all right. So there's MCSP. There was K capital T and K small t.
K small t
Doesn't enter into
doesn't enter into the picture right now.
Okay. And the reason why you talked about K capital T now instead of MCSP was why?
Because the intuition is the output of a pseudorandom generator has got low time-bounded Kolmogorov complexity because we're producing it from a short input quickly. Now, actually, this is where we really need a pseudorandom function generator, but I'm glossing that under the, sweeping it under the rug. Okay, but that's the intuition that being able to say something about time-bounded Kolmogorov complexity kills off pseudorandom function generators, and therefore kills off any hope of cryptographically secure functions. Since you brought up K little t, this is time to mention rather quickly, because I'm not going to go into more details. There's lots of other pseudorandom generators. In particular, there's something called the Babai-Fortnow-Nissan-Wigderson generator, which in turn is built on the Nissan-Wigderson generator, another generator that's got a lot of nice properties where you can play this game again, and you can show here the following. MK little tp, this is Levin's notion. This is computable in exponential time. which you can kind of guess because it's related to circuits that have an exponential time oracle. And again, I didn't give you the proof of that, but it's, once you know the statement of it, you can actually prove it yourself pretty quickly. But this trick that we had to compute F, for the Hill generator, we were trying to invert F. But this generator works for absolutely any Boolean function F, including a function, you know, that's just got one bit of output. And being able to compute F using the test that distinguishes random from pseudorandom, you know, there are some other steps there that involve some exponential time computation. But you can show, using similar techniques in some sense, using this other generator, that this is complete for X under P Pauli reductions. So it's the same notion of reducibility, except Turing reducibility means you can ask a bunch of questions, and the reductions being computed by circuits. And there is, I'll just write it this way, MCSP with a QBF oracle. Or here, instead of MK little TP, we could have also said MCSP with exponential time oracle, which is roughly the same as that. These are both complete. MCSP with a QBF oracle. QBF is the standard complete problem for P-space, is also complete for P-space under the same notion of reducibility. So with results like this, you can be tempted to think, these MCSP problems ought to be complete. You know, this one is complete for an important complexity class under reductions computed by small circuits. This one's complete for another important complexity class under reductions computed by small circuits. MCSP with no oracle ought to be complete for NP. Well, we are very far from being able to prove something like that because the techniques that are used to prove these results require that F have some nice properties that things inside NP don't seem to have, particular self-reducibility, in particular for this result, and some other things that really only kick in when we're talking about exponential time. So it's not really clear if this is telling us anything about what ought to be true at the NP level, except, you know, it suggests that these problems maybe ought to be complete. But interestingly, this is not complete for P-space under, let's say, log space reductions, even pretty general log space reductions. And this one is not complete for X under, let's say, the usual polynomial time M reductions, and you can generalize that quite a bit. So in other words, yes, they're complete, but also no, they're not complete. They're not complete under the usual types of reductions that we use in studying some of these complexity classes. So with that intuition, then you'd think, well, maybe we can prove that these problems are not NP complete under the usual reductions. You know, instead of getting, if they're complete, then something that we think is true happens, maybe we ought to be able to prove if it's complete, then something we don't think is true happens. But currently we don't have any theorems like that, unless you really restrict the notion of reducibility. I've only got 15 minutes, which means that I'm going to really have to move quickly. But some of these results are not too hard to prove. So we did that. Let's do this. Although if people have questions, they're very welcome. Please ask. Was there a question? No. So, I'm going to prove this one now. This is a lovely result due to Ryan Williams and Cody Murray. If MCSP is complete under your favorite notion of reducibility, then X is equal to ZPP. So assume X is equal to ZPP, and remember ZPP is in P poly. And let's also assume that let's say the satisfiability problem polytime reduces to MCSP. We're going to conclude that non-deterministic exponential time is equal to exponential time. Oh, but exponential time is equal to ZPP, which is contained in RP, which in particular is contained in NP. And we know by the non-deterministic time hierarchy theorem that NP is properly contained in NEXP. So what I need to do under these assumptions is prove that NEXP is equal to X, and then we'll be done. Is the strategy clear? Okay. So I want to take an arbitrary problem in NEXP and reduce it, put it into exponential time. So let A be in NEXP. Let's let B be equal to the unary version of A, which in other words is 0 to the X such that X is in A. Everybody understand what they mean by the unary version? Well, now, actually, I'd like to be able to conclude that this is in NP. I can only do that if A is in non-deterministic time 2 to the order n. But in fact, if I can do this for A in non-deterministic time order to the n, then I still can conclude NEXP is equal to X. So that's what I'm going to assume, which means that I can conclude that this set is in NP. And if that went by too quickly, just know, okay, I'm lying a little bit here, but I'm not lying in any big way. Okay? So we've got this unary set in NP. And since SAT is reducible to MCSP, everything in NP, this also, polytime M reduces to MCSP. So we've got this reduction. Let's look at what that does. We get input to the X here, and this reduction produces output some truth table F and some threshold. Now notice, let's call this f sub x because it's a function that's determined entirely by x. It's the output of this reduction. On input x, we're outputting this thing. Also notice that if I'm given x, in exponential time, I can certainly build this padded thing. And then I can run this polytime reduction. That's still just going to take exponential time. So this whole reduction is computed in exponential time. Oh, but exponential time is in p poly by our assumption. Which means that this function, f sub x, is computed by a circuit of polynomial size. Right? Because it's computed, given x, I can build this entire truth table. I can get any bit here via an exponential time computation which can be mimicked by a polynomial size circuit. Which means that this threshold, there's no reason for it to be any bigger than n to the L. Right? Because if you used a big threshold, the answer is just always going to be yes. Because it's computed. We know that this thing is computed by a small circuit. And so the only way we're getting any mileage from this reduction is if the threshold itself is small, and we're just trying to detect. Oh, but if the threshold is small, then this is easy to compute. Because in deterministic time, 2 to the n to the L, I can try all of the small circuits and figure out if any of them is computing this. Which means that I've got a deterministic exponential time algorithm for next, and we're done. Now that went by a little bit quick, but it had to. But I don't want to waste everybody's time. Did that outline make sense? So it's got a lot of assumptions. In fact, x equals VPP is a very strong assumption, although we can't disprove it. We know that that's in p poly. If SAT is, if MCSP is NP complete, then we get next was equal to x, and that's our contradiction. So we've proved this. And actually, the proof of this result is sort of similar. It uses a bunch of other machinery. In particular, there's an important theorem that says if B is any set at all, is hard for TC0 under AC0 M reductions, and let's say uniform AC0 M reductions, then B is hard for TC0 under length increasing uniform NC0 reductions. Now this is a little bit remarkable because AC0 reductions, each bit of the output can depend on all the bits of the input. But we're saying, no, you don't really need to do that. There's this other circuit that computes a reduction where each bit of the output just depends on a constant number of bits. Furthermore, it's a length increasing reduction. So, under this assumption, if MCSP is hard for this tiny class, under AC0 reductions? Well, we know it's also complete under these uniform NC0 reductions, which means that, in particular, if I want to compute the parity function of x, because that's in TC0, if I want to compute the parity function, I can reduce it to MCSP via this uniform reduction where each bit of the output depends on only a constant number of the bits of the input. And that also corresponds to this field of the output that's given what this threshold is. Now this threshold is just a log n bit number, which means that there's order log n bits of the input at most that affects this threshold. So by setting some of these bits of the input, I can fix this. And so non-uniformly, let's just set this to be the smallest number it can possibly be. And now I have a non-uniform NC0 reduction that's reducing parity on, let's say greater than or equal to n over 2 bits. It's still parity on quite a few bits, where this threshold is really small. And now comes the other nice idea, observation. If the threshold is small, then MCSP, let's say, with a small threshold, has small AC0 circuits. Why is that? If the threshold is small, well, it's like what we just did in the previous result, where we said that that circuit had size polynomial. Well, if the threshold is small, all we need to do is have a big OR over all small circuits. And for each circuit C here, we're doing an AND to make sure that all of the bits, that the function computed by C agrees with this function. And so, maybe this takes, the size of the threshold would be something like n to the epsilon, which means that this circuit here has size 2 to the n to the epsilon, but we know that parity actually requires circuits of size 2 to the n to the, something that depends on the depth. So just by looking at the depth of this circuit and what we can say about the size of that threshold, we get, actually I'm getting ahead of myself. What am I trying to do? Okay, this function A, this f of x, okay, the smallest it can possibly be is n to the epsilon for some epsilon. Because if it's smaller than that, we get small circuits for parity. And small circuits for parity don't exist. But each bit of f of x is computed by this uniform AC0 circuit. And I didn't really tell you what the uniformity is, but it's like uniformity so that this function ends up being in the polynomial hierarchy. Before we said that function had to be computed by small circuits. Here we're saying, it's got to be in the polynomial hierarchy. And if this is, so let's take a negative, something that's not in the parity function, which is like all the input is all zeros, that has an even number of ones, then figuring out what this bit of f of let's just call it f sub n is going to be a language in the polynomial hierarchy. And if it had small circuits, then this reduction wouldn't be working properly. I've kind of used up all my time, but that's the way that this works. And if NP were in P poly, then that means that the entire polynomial hierarchy would be in P poly. And again, just as in the proof up here, the reduction breaks. And in many ways, the proof of this is very similar. What I didn't get to at all was actually something that I have much more involvement in than the results here, which is the actual hardness result. And it's really easy, it's really simple. I'm sorry I don't have time to do it, but I think we probably should let you take a break. So that's the end of the lecture, except for questions.
Questions?
I have a question about the proof is the conclusion that X is not the ZPP.
Yes?
Is that in the proof somehow used that we use class ZPP, or it can be used in a class which is in intersection of NP and P poly?
Actually, you can prove something somewhat stronger here. So what you really get is if every sparse, or even, let's just say every sparse set in NP is reducible to MCSP via a polytime reduction, then X is not equal to NP intersect P poly. But in some sense, the most interesting things that are sitting inside NP intersect P poly would be RP, but if X were equal to RP, would be equal to ZPP. And so rather than make the statement of the theorem longer than necessary, we did this version. But yes, all of this is in the Murray-Williams paper. Question?
Yeah, this might be a basic question, I'm not sure, but MCSP, is that NP complete if and only if MKTP is NP complete?
This is a great question, and we don't know it. In fact, the situation is even much worse. I look at MKTP with one choice of universal machine. Well, that shouldn't really be any different than MKTP with another choice of universal machine. We don't know any reductions between these. Oh, there's also MCSP with, let's say, number of gates is the number of wires, or number of gates is the size, or MCSP with the number of wires being the number of size. Or you can change the type of hardware that you're using. Or you get all of these problems that should be the same thing. We don't know reductions between any of them. On the other hand, all of these theorems work for all of them except this one. This one has got a much tighter dependence on the threshold. And during break, I can sketch to you the way that proof goes, or to anybody, because it's really very easy, but it really has a very tight dependence on the threshold. All these other results, and even this result to some extent, carry over to certain approximations to the circuit size complexity or to the KT complexity. And together with an REU student, with 2 REU students from last year, we've got a paper showing that if we're looking at AC0 reducibility, AC0 reducibility to approximating the circuit size or approximating the KT complexity, you can't reduce even the parity function to that approximation if the approximation is more than just a constant. Which in particular, remember for different notions of KT complexity, if you change the universal machine, that already, as far as we know, can change the complexity by more than a constant factor. So, as far as we know, reducing something to one of these problems cannot be reduced to each other via uniform AC0 reductions. And in fact, you can't even reduce the parity function to it. And these functions, are as hard as anything that's in crypto. So you just can't reduce much to them using these simple reductions. Which means that they shouldn't be NP complete, but we can't prove it yet. But I think they probably are NP complete if you allow something like p-poly reductions. And that would be a wonderful theorem that we don't have any sense why that should even be true. It's just a gut reaction, and my gut has been wrong many, many times. Yes?
So this term here that you were about releasing the complexity of the reduction for arguments and pieces.
I'm sorry.
This theorem here, which is deleted. Yeah. Right here. No, down. Yes.
Oh, the one that's kind of erased.
That is it true for any B, or is using some specific feature of SP?
This theorem is true for anything. If you're anything at all that's hard for TC0 under AC0 reductions, then you're also hard under length increasing NC0 reductions. So in particular, there's something that builds on this, and its final and best form is in a paper by Manindra Agrawal that shows that for all the complexity classes that you care about, like NP or P or P space or anything that's closed under TC0 reductions, which is all these classes, there's essentially only one NP, there's only one complete set. All the complete sets for that class are isomorphic under uniform AC0 computable bijections. So,
we are not using anything specific of MCSP.
no, that doesn't depend on MCSP at all. Anything else?
So I didn't quite understand. So if you would have, so for example, for this MKTT, so we actually know that they don't, or we don't know actually that they are isomorphic, but they would be isomorphic if they would be actually complete for TC0. Is that right?
If these were complete for NP or P or TC0, if they were complete, then they would be isomorphic.
But do you think it's true or not?
I have a hard time believing that this is isomorphic to SAT. It doesn't look the same at all.
Other questions? Well, Thank the speaker.